Hi, I'm Thuy-Duong Vuong. I usually go by June. I will represent our paper on fast parallel sampling algorithm for discrete distributions. This year, Joy worked with my advisor Nima Anari, Yizhi Huang, an undergraduate student at Tsinghua University, Tianyu Liu, a postdoc at Stanford, Brian Su and Katherine Yu, who are undergrads from Stanford. We consider the problem of sampling from a density function mu, which defines a probability distribution p mu, where p mu x is just the normalization of mu, so mu of x divided by the partition function of mu, which is the sum of mu of y for on y. The reason we don't assume mu is normalized is because in many settings, you only have access to the unnormalized density function. For example, if you want to sample uniformly from the set of all spanning trees in a graph, then the density function mu is just the indicator function that maps the subgraph to 1 if it is a spanning tree and to 0 otherwise. On the other hand, if we want to normalize mu, then we need to know the number of spanning trees in the graph. We will see later that this task of counting the number of spanning trees in a graph is as hard as sampling a random spanning tree in the graph. One more thing, so we want to approximately sample for mu, meaning we want to sample from p mu hat that is close to p mu in total variation distance. Note that for practical purposes, this is as good as exact sampling for mu because any downstream applications with small polynomial runtime cannot distinguish samples from mu hat versus sample from mu. For mu supported on a discrete set, we can always convert mu to be a distribution over the n-dimensional hypercube minus 1 to the n. So from this point, we assume mu is supported on the n-dimensional hypercube. Now we talk about parallel sampling. The goal of parallelizations is to reduce runtime by distributing work across many machines. Our goal in this work is to reduce the parallel time to quasi-constant of polylog time while using a reasonable number of machines. Whether a fast parallel sampling algorithm exists is an old question raised by Mumuli, Vajirani, and Vajirani in 1987. There has been recent interest in parallelizing sampling algorithm because modern computer architectures is highly parallelizable. A popular method to sample is to run a Markov chain or random walk, but this often takes at least linearly many steps in the dimension to produce a good sample, so Markov chains is not usually a fast parallel algorithm. There are some attempts to parallelize Markov chains, but those only work for restricted cases. And actually, there are no barrier against parallelizing Markov chains in general. This was discussed in a work by Tsinghua 10, where he shows that the Jerome-Sinclair Markov chain to sample perfect matching cannot be very efficiently parallelized unless polynomial time algorithms are all parallelizable. So we need a new direction to get a fast parallel sampling algorithms aside from parallelizing Markov chains. Many distributions that we want a fast parallel sampling algorithm for already have fast parallel counting algorithms. By counting, I mean evaluating the partition function of mu, which is the sum of mu x over on x. By fast, I mean in NC time, meaning there's a parallel algorithm that needs poly-n machines and polylog n parallel routes. Sampling and counting are equivalent due to a classical result of Jerome Valiant Vajirani. This means you can design sampling algorithm given a counting oracle and vice versa. But the JVV sampling to counting reduction takes at least linear in n many sequential steps. Let me tell you briefly how the traditional JVV reduction works. Let's say you want to sample spanning trees on a graph. First, know that the probability of a random spanning tree containing an HE is the number of spanning trees in the graph containing E divided by the number of spanning trees in the graph. Starting with an HE1, you can use the counting oracle to compute the probability E1 is contained inside a random spanning tree and flip a coin to determine whether to include E1 in your sample spanning tree or not. Suppose you do include E1, then you can look at the HE2 and compute the probability of including E2 conditional already including E1, then flip a coin on whether to include E1 to include E2 or not, and so on. It's easy to see that this reduction needs to take time linear in the number of edges, which is not what we want. So can we get the reduction from sampling to counting that runs in faster parallel time? Our work saw the first quasi-random NC time reduction from sampling to counting for distributions whose tilts have boundary covariance, and I will define what this means later. By quasi-RNC, I mean the parallel time is still polylog n, but the number of machines used is quasi-polynomial in n, so n to the log n. Here, we assume the counting oracle and compute the mean of the tilts of mu, which can be done if we can compute the partition function of all tilts of mu. As an aside, in a subsequent work, we can reduce the number of machines to polynomial. In this work, for a class of distribution that satisfies a stronger assumption called transport stability, we can also reduce the number of machines to just polynomial. This class includes familiar distribution, such as the uniform distribution over spanning trees of a graph, or generally strongly Rayleigh distributions. It also includes strongly Rayleigh distribution under partition constraints, where the number of parts in the partition is constant. Let's talk a bit about the applications of this main theorem. Our main theorem implies past parallel sampling algorithm for random spanning tree and random directed Eulerian tour. Spanning tree is a familiar concept. So it's just a cyclic connected subgraph of a graph. So here's a picture of a spanning tree. I'll quickly define Eulerian tours. A directed Eulerian tour of a directed graph is a directed walk on the graph that uses every edge exactly once. The nice thing about these two distributions is that the counting oracle can be implemented in NC time. This combined with our main theorem gives an RNC sampling algorithm for spanning trees and a quasi-RNC sampling algorithm for directed Eulerian tour. Our results apply more broadly to a cluster distribution called determinantal point processes. You can refer to the paper for the definition of this class. Now we can define what tilts of mu having boundary covariance mean. The tilt of mu by a real vector y is the reweighting of the density function mu by a log linear function defined by y. More precisely, tau y of mu at x is exponential of the inner product of y and x times mu of x. Boundary covariance means the covariant matrix of mu is upper bounded by some constant times the identity in the PSD sense. The condition we need is covariant of all tilts of mu are bounded by a constant time the identity. And the previous work already showed that for determinantal point processes, which include the uniform distribution over spanning trees and over directed Eulerian pools, we have this property. More precisely, if mu is a determinantal point process with symmetric or non-symmetric positive semi-definite matrix, then the covariance of all tilts of mu are bounded by a constant time identity, and the counting oracle for all tilts of mu can be implemented in NC time. Thus, mu had a quasi-RNC time sampler by our main theorem. Now I can show you how the new sampling to counting reduction works. The first idea is to turn discrete distribution into continuous distribution by adding Gaussian noise. More noise equals a distribution that is smoother and easier to sample from. The next question is, how can we go from the easy or high noise regime to the low noise regime? There's a tool that does precisely that. This tool is stochastic localization. Stochastic localization is a continuous stochastic process, but we cannot implement a continuous process on a computer. We need to discretize it somehow. Our framework is a logless way to discretize stochastic localization. And now we can go into details about turning discrete to continuous distribution by adding Gaussian noise. As I mentioned, adding Gaussian noise to a discrete distribution will make the distribution smoother, like we make the variance of the Gaussian noise increase. For intuition, Consider this toy example of the uniform distribution on the four corners of a square. If we add noise with a small variance of 0.3, then the convolved distribution has 4 spikes on the corner of the square. When we increase the noise level to 0.5, the spikes become less prominent. When the noise level is further increased to 1, the distribution becomes smooth and in fact strongly log concave. This fact holds more generally for all distributions whose tildes have bounded covariance. If mu and all tildes of mu have covariance being bounded by a constant times the identity, then adding Gaussian noise with constant variance to mu results in a well-conditioned strongly log concave distribution. The nice thing about such well-conditioned, continuous, strongly log concave distribution is that we can easily and efficiently sample from them using existing algorithm. So the next question is, given sample from the noisy distribution mu convolved with Gaussian noise, how to generate sample from the original distribution mu using stochastic localization? So here's the algorithm. We should think of sample from the convolved distribution as the vector y defining the tilt, and the discrete distribution we want to sample from in each step is tau y of mu. The algorithm starts with y0 equals 0. For I from 0 to t minus 1, sample tilde x from the tilt of mu by yi convolved with Gaussian. Then set yi plus 1 to be yi plus x. Finally, the algorithm outputs the sign of y bit t, which is an n-dimensional vector with plus 1 or minus 1 entries. Note that here all the vector additions can be done in parallel by having one processor keeping track of one coordinate, so you need n processors in total to handle vector addition. Recall that this highlighted distribution is well-conditioned log concave. We will see that the step of sampling tilde x is also just vector addition plus oracle access to the gradient of this convolved distribution, and the gradient can be computed using the counting oracle. It's not hard to show that all entries of y bit t have a magnitude of roughly bit t, so the output vector v is roughly y bit t divided by bit t, and is distributed at mu convolved with a Gaussian with variance 1 over t. As t goes to infinity, this convolved distribution is just mu itself. But our algorithm cannot run forever, so we need to make t finite. We will set t to be log n, and this is good enough. The reason is for t equal log n, with high probability, all entries of a vector sample from the Gaussian with variance 1 over t will be much smaller than 1, making the convolved distribution close enough to mu in total variation distance. So now we got an algorithm that runs in log n steps, and each step can be implemented in polylog n time using the algorithm by Sen and Lee to sample from continuous strongly log concave distribution. Now we discuss how the Sen and Lee algorithm fits into our framework. First, we need some background on continuous distribution. A distribution mu on the real vector space is well-conditioned log concave if the Hessian of its density function is upper and lower bounded by a positive constant times the identity. For mu whose tildes have bounded covariance, convolving mu with sufficiently noisy Gaussian results in a well-conditioned log concave distribution nu, and we can sample from a distribution nu hat close to nu in Wasserstein distance. Transport stability of mu is the precise ingredient we need to translate this bound in Wasserstein distance of the external fields to a bound in Wasserstein distance of the tilted distribution. By induction on the iteration, we can get a bound in Wasserstein distance between the distribution of the output and the target distribution mu, which can be translated to a bound in the total variation distance between the distribution of the output and of the target distribution mu, using the fact that the hypercube is discrete. For general distribution mu on the n-dimensional hypercube, We can always make this constant C in the definition of transport stability to be n. But for strongly related distribution, we can make C to be a constant. The number of machines depend on C raised to the number of iteration T, which is C to the log n. So that's why for general mu whose fields have boundary covariance, the number of machines we need is n to the log n. But for strongly related distribution, we get constant to the log n, which is poly n machines. Where if we use the counting oracle? For continuous sampling, we need to evaluate the gradient of the log density function, which is just the mean of the fields of mu, plus some constant. This gradient of the log density function is also called the score function, and it appears in recent works in machine learning about sampling or generating data using diffusion. And diffusion is a process that is very closely related to the stochastic localization process we use in this work. So we obtain quasi-RNC sampler via parallel sampling to counting reduction for a certain family of distribution. In follow-up work, we remove the quasi part and get a true NC time sampling algorithm which use polylog n routes and poly n machines. So some open problem. Can we remove or weaken the assumption that we need all tills of mu to have boundary covariance? And secondly, can we use a weaker counting oracle that can only compute the mean of partition function of the conditionals of mu instead of the tills of mu?